Ever wondered why some AI systems miss the outliers in a network? Like why a recommendation app might ignore your weird but awesome hobby? Today, we're diving into a sneaky problem in AI called degree bias, and why it matters for everything from medical diagnoses to your next Netflix binge. So here's the deal. AI models analyzing networks, like social media connections or scientific papers, often struggle with nodes that have few connections. Think of it like trying to guess someone's interests based on just one friend in a social network. These low-degree nodes are hard to read, and traditional models tend to overlook them. But what if we could make AI better at spotting these hidden gems? Let's start with the problem. In graph neural networks, nodes with many connections, high-degree nodes, dominate training because they have more positive pairs, similar nodes to learn from. Low-degree nodes, though, have sparse, noisy neighborhoods. Imagine a conductor surrounded by producers and directors. Their neighbors are all over the place, making it hard for the model to learn meaningful patterns. This creates degree bias. Models perform way better on high-degree nodes, like the popular kids in class, but fail to capture insights from underrepresented ones. Why does this matter? Picture a medical AI that misses rare diseases because it's focused on common ones. Or a streaming service that ignores your niche tastes. Degree bias isn't just a technical glitch, it's a fairness issue. It skews results, leaving critical data underrepresented. But here's the breakthrough. Researchers have developed SHARP, a framework that tackles this bias head-on. Let's break it down. At its core, SHARP builds on HAR, hardness adaptive reweighted contrastive loss. Traditional methods like graph contrastive learning, GCL, create augmented views of graphs, training models to pull similar nodes closer and push dissimilar ones apart. But low-degree nodes often lack enough positive pairs to learn from. It's like trying to learn a language with only a few example sentences. HAR solves this by adding more positive pairs and weighting them based on difficulty. Think of it as giving extra practice to tricky problems. For example, if a low-degree node has neighbors that are confusingly mixed, like a conductor surrounded by producers, HAR flags those as hard to learn and gives them more attention. This helps the model focus on the most informative data, reducing bias. But SHARP takes it further. It extends HAR to real-world scenarios where not all data is labeled. Imagine training an AI on a mix of labeled and unlabeled data, like a teacher giving some answers but leaving others for the student to figure out. SHARP uses pseudo-labels, educated guesses for the unlabeled data, then fine-tunes the model. The result? A system that's fairer and more efficient, even with less data. The experiments? Mind-blowing. On 4 datasets, SHARP outperformed existing methods, especially for low-degree nodes. Take the Cora dataset, which analyzes academic papers. For papers with just one connection, degree 1, a standard model scored 0.71 accuracy. SHARP, it jumped to 0.81, nearly a 10% improvement. And this wasn't a fluke. The same pattern showed up across different datasets, even when models had more connections to work with. But here's the real magic. SHARP doesn't just boost accuracy, it understands the data better. Imagine training a robot to sort marbles by color. Traditional methods might just pile them all together, but SHARP creates clearer boundaries between groups, like spacing out red and blue marbles so they're easier to distinguish. This means SHARP isn't just making better guesses, it's learning more meaningful patterns. So what's next? While the field is still evolving, methods like SHARP are paving the way for smarter, more equitable AI. The math behind it. It's pretty wild, leveraging contrastive learning with dynamic weighting and pseudo-labeling to balance fairness and performance. If you're interested in the details, check out the paper linked below. And if you want to dive deeper into graph neural networks, hit subscribe. Thanks for watching, stay curious, and let's keep pushing the boundaries of what AI can do.